So the circuit shown consists of an ideal battery, a 2 ohm resistor, and then two other resistors, R1 and R2. Each of those is unknown, but we know the sum of those two resistors is 8 ohms. So they're in series, that means they just add together to give you the 8 ohms. And we also know that there is 4 amps of current passing through that 2 ohm resistor. So part A, is it possible to calculate the EMF of the battery? That's the potential difference across the battery between this point and this point. And the potential difference between those 2 points is going to be the same as the potential difference from this point to this point, because that resistor is connected in parallel with this battery. So since we know the current and the resistance, we can easily calculate the potential difference using Ohm's law. Delta V is equal to I times R, and you get 8 volts of potential difference across this resistor, which means we have 8 volts across the battery, so the EMF of the battery is 8 volts. And in part B, is it possible to calculate the current through the battery? Well, we already know the current through this resistor, and we would need to figure out what is the current passing through this branch of the circuit over here, because whatever current comes out of the battery over here, when the current gets to this junction point right here, some of the current splits and goes down this way, which is 4 amps of it, and some of the current splits and goes this way. So as long as we could figure out how much current this is, we could say this current plus this 4 amps of current would equal this current coming out of the battery. And it turns out we can figure out this current because we know the total potential difference across this combination of resistors from right here to right here is 8 volts, because that combination of resistors is still connected in parallel with the other resistor and with the battery. Even though those two resistors together, they're in series with each other. The combination is in parallel with the rest of the circuit. So, knowing that we can take Ohm's law and for I is equal to delta V over R. The delta V was 8. The resistance of the two combined, so that's R1, 2 combined, is 8, because it said they add up to 8. So that means we have 1 amp of current in that part of the circuit. So this is 1 amp, this is 4 amps, which means that coming out of the battery was 5 amps of current. And part C, is it possible to calculate the potential difference across R1? Well, we know the total potential difference across both of these resistors combined, which is 8 volts, but that could be split any possible way depending on the values of R1 and R2. So we cannot get the value of the potential difference just across R1 because we don't know how that 8 ohms is divided between these two resistors. On the back of the page, part D, we're now going to swap resistors 1 and 2. Does that change the current in the right branch of the circuit, which is where those two resistors are located? And since those resistors are in series, which means you just add them together, addition is a commutative property, so that would not change anything about it. We would still come up with a total of 8 ohms, meaning that we would still have 1 amp of current in that part of the circuit. But suppose instead, for part E, that the R1 and this 2 ohm resistor are swapped. Would that change the current? And the answer is that we cannot really determine it, because now we're changing, if this is a pretty small value that we're swapping over here, that's going to make a big difference in the resistance. But if it's a larger value, that wouldn't change the resistance as much. We, based on the fact that we don't know how this resistor compares to this resistor, there's no way to know what's going to happen with that current. So now all resistors are returned to their original locations, and you are now told that the R1 and R2, the values are 1 ohm and 7 ohms. And we just want to calculate the numerical values of the current and potential difference across each of the 3 resistors. So since we're looking for specific numerical values, this is where it's probably just easiest to set up a VIR chart and just begin filling it in. So we need 1 row for each resistor, R1, R2, and I guess I'll just call the 2 ohm resistor, I'll just call that R3. I'll label it on the diagram. And we need the last row for the total. So we know the three resistors are 1, 7, and 2. We know the current through the R3, the 2 ohm resistor, is 4. I need to label this as VI and R. We know we've already figured out the voltage across that resistor and the total voltage, and we can get we know the current through R1 and R2 are both 1 amp, and we know the total current flowing out of the battery was 5 amps, so we pretty much already got most of the table filled in. The only thing left that this question is asking for is what is the potential difference across R1 and R2, and we can just use Ohm's law, so I times R, and so that would give you 1 volt across the 1 ohm resistor, and 1 times 7 gives you 7 volts across the 7 ohm resistor. And in part G, if the battery starts with 12 kilojoules of available chemical energy, so we're going to say the energy is 12,000 joules, and that can be converted into electrical energy. How long will the battery last? So this is power is equal to the dissipation of energy over time. We have to solve for the power, and that's just multiplying these two things together, the I times the V, so it's 40 watts of power. And if we rearrange the power equation for time, you get delta E over P, so it has 12,000 joules of power that it can lose, divided by the 40 watts of power, and that gives you a total time of 300 seconds. And if this were a multiple choice question, they might express the answer as 5 minutes.